Okay, let's get started. This will be my last lecture today. We've been talking, I'm going to talk about the Gimon transmon and an experiment that we did on this. And then I'll start at the end, talk a little bit about our quantum supremacy effort and why we're doing that. Why are we thinking about an adjustable coupler qubit? And you could see with the previous results with the XMON where we were moving the qubits in and out of resonance to turn on the interaction on resonance, bring it off resonance to turn off the interaction. And it works, and we can get that to work. But when we have to bring it off resonance by almost a gigahertz, you pick up a lot of phase when you do that. And it means you have to have very accurate control to make sure you know what the phase is. And that's a little bit tricky. It can be done. We want to look at alternate ways of doing it. Yeah, and I would say that's a generic issue in superconducting qubits. If you use fixed coupling, then you always are worried about turning on and off the interaction some way, and there's a lot of subtle things you have to do. Things are, kind of gets a little bit hard. So be able to control the interaction is actually kind of nice, and you can do some new and interesting things with it, which I'll discuss here. So what we have here is it's just going to be a 3-qubit experiment, and then we'll go on to more qubits. And what we're going to do, and I think this is kind of interesting, is we're actually going to use a quantum processor to solve a quantum chemistry problem. Now, of course, it's a toy. It's really simple, but we're going to actually find a real solution that, tells you something useful about it. And the mapping of the quantum chemistry problem will be the scattering of a sodium atom off a helium, and then we're going to want to know what's the chance of exciting the states of that sodium atom during that event. Okay, so we'll have to talk about how to map it and how to do that. So it's, I think, an interesting example. So let's just start with the physics of what we're getting at here. Sodium atom scattering off a helium, impact parameter at a few kilovolts. This is a classical in the non-relativistic limit. Here's an ion beam of the sodium and somehow in an experiment through the helium and measuring how it's scattering. The important thing here is to think of the energy levels of the system. The helium has a very deep 1s to 2s transition. We know that it's inert. This is such a big energy scale in the problem, we treat it inertly. So there's no internal dynamics to the helium. The sodium atom is much more interesting, being that it's an active atom. You have your 3s state, which is your ground state, and then your 3p excited states that are about 2 electron volts away. And this small energy difference is means that this is going to be the active energy that we're going to be considering here. The symmetry of this is that 2 are symmetric states here, so you really only have to consider 2 states. And what we're going to do is we're going to encode the system in a way that makes it easy to simulate, where if you're in the sodium, the sodium 3s state here, that will have an excitation in one of the qubits. And if you're in the sodium, one of the 3p states, that'll have an excitation in another qubit. And the third unique one will have the third qubit. So this is these states encoding into single qubits is a little bit inefficient, not necessarily scaling, but it's very efficient in terms of doing simulation, so we do it that way. Okay, and then when you scatter, these two systems can interact, and you can make transitions between these two states, or between the various states. Okay, so how does this work? Okay, you have the sodium and helium interacting with the velocity here, and at any moment in time there's a distance r between the sodium and helium, which is just a very simple classical formula between that. And given a distance between that, you have an interaction between the helium and sodium, which you have to solve in conventional quantum chemistry means. Okay, so you're going to have an energy levels for these three states, being in the ground state of the sodium and the excited states, which are given by U versus R. Okay, and you know, clearly when R is far away, R is big, you have some constant values, and then as R gets close and the electrons start interacting, you have a big change in U given by here. And then also there is an interaction where the states can couple to each other and given by these three interaction coupling terms right here. Again, the coupling is constant out here, and then changes going into here. So you can write all of this as a systo-Hamiltonian having to do with the energy level self-energies and all the couplings given by the off-diagonal elements here. And what is it? There are 6 unique elements to describe the 3-level state. And then you just say, given a function of time, as this comes closer here, these particular 6 terms here change as a function of time given by here. It's just a classical, it's just mapping that. Okay? Everyone clear with this? And so we have H as a function of time, and the quantum chemistry problem is to solve that. Okay? So it's just integrating the Schrodinger equation. I know it's only a 3x3 matrix. It's not very hard, but we're on it again. It's a toy problem. We're going to show how this works. You just have to integrate the Schrodinger equation to know what happened during the scattering event. So you just integrate this 3x3 matrix. That's what you're going to do. Okay, so the mapping it to our system, you have something into femtoseconds and electron volts. Okay, so the obvious thing to do is you scale the time and the energy. So you look here, I'm going to make the energy 10 to the 9 times smaller and the time 10 to the 9 times longer. So this is some scaling factor of H and T. So now you have something that's in the microsecond range and something in the megahertz range. And that's something, of course, we can solve with our quantum computer. Okay, now if you note here, everything's all kind of scrunched up, and it would be hard to get everything to work properly, you know, because all the interaction is happening really fast right here. So what we're going to do is make the scaling factor here a function of time. Okay, so it's going to be 10 mostly 10 to the 7. We're going to stretch it out here, and then when it's close to the interaction here, we're going to make it bigger. So you get to choose this lambda t, and then you take this, and you get this kind of form for the energies of all these 6 turns versus a time scale. Now it's 300 nanoseconds. That's way shorter than the coherence time of our devices. Everything will work nicely. Okay? And then these kind of energy scales, 30 to 50 megahertz, is something we can program into our system. Okay, so that's the mapping of the problem, so that's something that we can solve. Now what we're going to do is talk about the Gimon device given here on how to get the Hamiltonian so that we can do all this. So what we have here is this typical transmon Hamiltonian, kind of built in the Gmon, in the Xmon way, only it's an I instead of an X, but you still have all the same terms here. But the difference here is when you form this LC oscillator, you have the current that's flowing through this oscillator not just go to ground, but go through some inductors from here to here and then the ground. And these inductors actually look at the, effectively will couple to the 2 neighboring qubits. And so what we have, the couple from this qubit to this qubit, it's inductor-inductor coupling. This kind of coupling is kind of similar to what you would get for capacitor coupling, where you would get this kind of swapping interaction. It turns into the same thing. But what we have here is a secondary loop here with a Josephson junction that acts as a variable impedance transform, a variable mutual inductance. So you can work through the physics of this. I'm not going to do that. But remember earlier we talked about the Josephson inductance is tunable with the phase across the junction. And in fact, this Josephson inductance blows up when the phase is equal to pi over 2. Okay. And what you do, for example, is you can put a flux into this loop here so that the phase across the junction is pi over 2. That means the inductance is infinite, and thus you'll turn off the coupling. If you put some flux into here and that inductance is infinite, you'll get no current here and no flux into here, no coupling. And it turns out that when you design it properly and work it out properly, you can change the effective mutual inductance here from positive to 0, like I said, and to negative. So I kind of think of it as you have these two loops where you would have, let's say, positive mutual inductance, and then electronically I can go to 0 or then go to negative mutual inductance. And for example, the negative coupling is when this actually forms a negative inductance, which when you look at those equations, it allows you to have a negative inductance. So we have a tunable coupling. And then this loop, we have a wire that comes into here. That's what, let's see, which wires? That's these wires right here that allow you to change the flux through here and give you the tunable coupling. So you can go ahead and measure the coupling between the two qubits. This is the coupler flux bias. You put in about a half a flux quantum into it, a fairly large amount of flux into this loop here. And you can go from a positive coupling here to a 0 coupling, and then here to a negative coupling just by doing that. And the important thing is that we can change the current into this loop, and thus the flux into here, on nanosecond timescales. We can calibrate it, know what's going on, move this back and forth in very, very short amount of time to do that. So in the end, what happens is you have a Hamiltonian where with the qubits you can change the frequency of the qubits in the normal way, putting it with a tunable like Xmon kind of qubit. We can change that. You can put on microwaves and make transitions between the 0 and 1 state at will, which is what this term is right here. And then we have this tunable mutual inductance, which has the swapping interactions, which is an XX plus YY, or alternatively, this is equal to sigma I plus sigma J plus sigma I sigma J plus. So this is just the typical swapping term with a term here that is completely adjustable, okay, within nanosecond time scales, as these are, okay? So it's nice. Fully tunable, controllable interaction. Now, this is all great. I would say the hard part of this experiment is actually calibrating all of this stuff and doing it in a clever way so you really know and measure what this is, and doing it so that when you put multiple pulses in here, you don't have crosstalk, and you know exactly what's going on. And you know that's what takes the time. That's like 90% of your time. Running the algorithm tends to be the easiest thing to do. And in some of the later Gimons, you know, we've worked this over years. It might take us a year to figure out all the subtle physics to calibrate it, and then in a couple of weeks you run the experiment. So it's not unusual for a quantum computer to be that. We're building an analog computer. It takes a lot of effort to understand what's going on. But in the end, you just have a model for what's going on, and then you can do whatever you want with it. Okay, and that's just, in the end, that's just a lot of good physics and a lot of software to make sure that that's doing. So kind of schematically, what we have is our 3 qubits, okay, which we can control individually, both the frequency and the excitation. Then we have a couplers between them, and we can control that. And these are the control sequence lines we're going to do for the experiment. So what happens to integrate the Schrodinger equation is we first put a pi pulse in Q1, and given our encoding, that's equivalent to saying that we're in the ground state, in the S state of the sodium. And then to simulate the collision, we change the frequencies of the qubits versus time, and then we change the coupling strengths between them to map to the 3x3 Hamiltonian for the system. So these are the control sequences. And then at the end, you measure the 3 qubits. And if it's blue, it's stayed in the 1s state of the sodium. And then if it's red or green, it went into one of the other 2 p states. So we want to know what's the chance, what's the probability that it actually did that excitation. Okay? So like I say, you spend a long time calibrating it, okay, and then you run the thing, and here's the results. You can see a few data points right here. 53%, 41% ground state, 53% one of the p states, 3% one of the other 2 p states. There's your answer. Okay? Now, okay, that's, how do we know it's working? Okay, you have to trust that it's calibrated properly. Okay? So what's actually kind of interesting is you can see what's going on inside of this system. Okay, when you do the numeric integration, you can numerically integrate to any time you want, stop it, measure the probabilities, and know that we can do the same thing experimentally. We run this experiment, run it to some amount of time, stop it, then do the measurement and see what the probabilities are. So we can look inside the collision just like you would do numerically. So if you do that experiment, and this is, of course, takes a lot more time and a lot more data, that's what you see. So you see initially it's in the S state, and then as it starts to interact, you get this really complicated interaction between the S and P, all the P states, due to the complicated Hamiltonian and blah, blah, blah. It does all that, and then it comes to the final answer once it's far apart again. Okay, so it's nice, at least you see there's some complicated dynamics going on. You can see what the quantum computer is doing. That's really great. Well, okay, does it make sense? And what you can do, of course, is compare at all these different times what would happen when you integrated the Schrodinger equation. So that's what I'm going to show next from the numerical results, which are given in the solid lines. And what you see is that there's a good correspondence between the experiment and theory. Even little dips like this, you see the oscillations go up and down together, and and then everything kind of levels out at the long run. It's really kind of remarkable. There's a lot of structure going on in here, to be able to get that right. Now, this is really nice. I have to stop at this point here and say we do not cheat here to get these good results. You calibrate and then you run. You don't look at these wiggles and say, oh, okay, this isn't wiggling right. Let me change these couplers a little bit to get it to match. Okay, we don't do that. Okay, we just calibrate very carefully and then run. Now, it's true that if you calibrate and doesn't match, then the student can't write his thesis. Okay, so you can't finish the project till you know what you're doing. But if it doesn't work, then it's like, okay, I calibrated wrong, and you go back and figure that out. And after a while, you figure out how to do everything properly and get all the factors right, and then you run it, and then it works. And that's how, of course, you want a quantum computer to work. And like I say, the hard part is figuring out like all the little things you have to do to get the calibration right. Okay. So questions on that? Yes?
Say it took you like a year to get the system calibrated. Is this sort of a one-off, or if you try to make another one of these Gimon circuits?
So what happened? Yes. So we do that and we learn all that, and then we go on to the next design, which I'm going to show you later. And then you take all that, and then you do that, and then we find, well, maybe our calibration wasn't quite as sophisticated, and then you build upon that, and you just kind of build and build as you're doing more and more. I would say the nice thing about this is it's kind of funny. It's a psychological issue. It gives you the confidence that if you just work hard and you just understand everything, then it's going to work out perfectly. Okay? And you know, when you do an experiment, you hope that's the case, but that's kind of what happens every iteration. So, you know, but yeah, we learn from that. But, you know, we then go on to the next thing. Okay, what people are interested in chemistry is actually the cross-section of it. So you want to know the probability that it's excited, the probability of impact goes as this impact parameter B dB. You have to integrate, so you have to do this for a bunch of different B's. Here's the numerical calculation versus velocity and versus the impact parameter. The color is the probability here. This is what we did the simulation, which you see matches qualitatively very well with what's going on here. And then if you actually do the quantum simulation and do that integral, you get the blue right here. Numerical computations, very close to that right here. And in fact, in the 1977, when this was done, they actually measured this. But there's big uncertainties on the experiment. It's very hard to do. So this is very close to numerical simulation. Makes sense. It works well for a variety of parameters, is what you see there. Okay. So I'm going to move on to a second experiment. A very interesting thing you can do with adjustable coupler is to have, synthetic gauge field for photons. It's this fancy word right now. And what it means is that normally when we have this G, you have a sigma plus, sigma minus coupling between the two. This is normally a real quantity. You can actually build couplers that the coupling strength is actually a complex quantity. So we were talking about either positive or zero or negative. You can actually make it a complex quantity. And for example, if you want to talk about the effect of a magnetic field on electrons, you can have phase factors that are in the various coupling terms, and you want to be able to kind of simulate and be able to do that. And it turns out with an adjustable coupler, it's a very natural way to do that, and you can see some very nice physical effects. So normally what happens is we have two qubits, we have adjustable coupler, and what we can do in this experiment is we just set this the coupler as, let's say, 2 megahertz, and then what you do is you do this swap kind of experiment that I've been showing before. And what you do is you put an excitation on one of the qubits and then look at versus time, which is right here. It's a swapping time. It's going to swap back and forth. At the end of some time, you measure the probability here, and you see that it goes from probability to 1 to 0 to 1 to 0 because it's swapping, state of swapping between these two here. And of course, when it's detuned, exactly tuned up right, you get the maximum swapping, and then as you move away, you get the chevron curve that I was talking about earlier in this. So that's the typical swapping experiment here. So what we're going to do here to investigate this kind of coupling term is we're going to take our adjustable coupler and we're going to modulate it in time with between positive and negative values with a G naught here, that's now 4 megahertz, and we're going to modulate it as cosine of omega 12 t, where omega 12 in this case is 35 megahertz, and there's going to be some phase factor here, which for here doesn't matter, but later it matters. Okay, so we know what G is a function of flux, and we just program in some flux function that is going to give us exactly this. So here's the theory behind making this. We have G0 cosine of, what am I calling that? Omega 1, 2t. I'm going to forget about the phase factor for now. Okay. And that's equal to G naught over 2 e to the I omega 1, 2t plus e to the minus I omega 1, 2t. Okay, there's the theory. That's all you need to know. And what happens is this thing is creating sidebands of the coupling at the oscillation frequency of the G of plus frequency and minus frequency. Okay, and notice that because of from cosine to this, there's a 1/2 factor here. So we have that as the Hamiltonian, and what it means is that when you have a 1, 0, and 0, 1, there's going to be a sideband at omega at 35 megahertz, according to here, and it's only when the qubits are detuned by 35 megahertz, with the detuning plus this offset of 35 megahertz, it'll then be on resonance. Okay? So here we are, we're doing the same swap experiment here, only here we have a constant delta 1, 2 at 35 megahertz, and here I'm adjusting the frequency right here. And you see when you have 35 megahertz oscillation of the G, okay, you then get a swapping interaction that's on resonance, that goes between 1 and 0 and 1 and 0, just like what you're seeing here. And you note that G0 was 4 megahertz, and this is the same period as this, which was 2 megahertz, because of that 1/2 factor. Okay? And if you look at the two curves, they look very, very closely the same. And the point I want to make here is that we can build this adjustable coupler and make it with good fidelity. There's nothing going on wrong here, right? It's working really well. So you can do high quality experiments, because this is just as good as this. Okay, so you can really see the physics well. Now, in this particular experiment, just coupling two qubits, we set the phase equal to 0, but it turns out you're going to see the swapping no matter whatever that phase is. You have to set up another experiment to see the swapping. So we have any questions on that? Yes?
What happens if your omega 1, 2 becomes too high, or if you change from cosine to some other way?
Yeah, so if omega 1, 2 becomes too high, everything should work until maybe at a high frequency you won't know what the waveform looks like, very well. Or if you don't have it calibrated right, you think you're programming a cosine, but it's going to have some harmonics in it. And then you're going to see some other sidebands. And obviously there's two sidebands here. So you're trying to be on resonance with this, but if you don't set up the experiment properly, you might see sideband thing here, because there's two resonant conditions. So you kind of have to do the experiment properly so that you're dominating this. So you give yourself, when you turn and on and off these couplings, you do it with a little bit of a gentle. You don't turn on and off the offset suddenly, but you might put a little slope to it, and that controls the spectral weights so that you make sure that you aren't going to couple to these other modes in the way that we were talking about the two-state leakage problem. So you have to do things like that to make it work properly. But these are all kind of standard tricks you do with all your control pulses. Good. Yeah, there's another resonant conditions here, and there can be other things. So you have to do that right. But I would say once you control the G versus flux, you know that, and then you just write some inversion program to give you that cosine. And then it's pretty clear, pretty, I think. If you were to just modulate the flux with the cosine, it wouldn't be as good. Okay. So let's do something interesting. What we do is we have our 3 qubits here, And we are modulating these couplers according to this, this term here. And they're three different frequencies. And we having it so that they're going to couple to each other with this phase-dependent way. And now, because we have three phases in a loop, you can define, it's actually the total sum of the phases, which an effective flux, normalized flux in between these loops. And that flux is going to give you some interesting physics in the way that, you know, if you're looking at the phase of electron, it's kind of the loop, the phase around a loop that matters. It's a typical way. So we have these three phases that we can adjust. And what we're going to do here is adjust the case. This is the case, I'm going to do this first, where the phases, its effective flux here is 0. These phases are set to 0 or 2 pi, or a multiple of 2 pi. And what we do here in the experiment is we first put an excitation in Q3, okay? And then because this is a symmetric case, we look to see what happens at time. If we have an excitation in here and everything's symmetric, the excitation is going to move to the other two, and then it's going to reflect back. And that's what you see, that this probability goes down, the green and red probabilities go up, and then it just oscillates back and forth over time. Okay? Now what happens is, much more interesting things happens at a flux of pi over 2. Okay? And in that case, you have excitation here in the blue qubit. That excitation goes away, but the excitation now has a direction to it. Okay? You've broken kind of the symmetry of it with this phase, and now it has a direction where the excitation is going to go preferentially to the green, which you see here, and red is very small. And then it's going to continue to rotate to the excitations to the red and to the blue. So this excitation is rotating around in this direction. Okay? And then if you do this minus pi over 2, you would guess from symmetry, okay, that it's going to do the opposite thing, which it does. So it's blue, and now instead of green, it goes to red, and then it goes to green. So it's circulating around in the opposite direction. Okay. So that shows you've broken that. You have the effect of the gauge fields. You can see circulation. And you see the data is pretty nice. The coherence is pretty good, even at hundreds of nanoseconds. So the coherence of the Gimon devices are about 10 microseconds or so. A little bit worse than the Xmons in these initial devices, but very close. Okay, so that's nice. Now I want to ask a question. I've put one excitation and it's rotating around. If I were to put two excitations, okay, what would happen? And remember, you can't put one excitation here, one excitation here. You can't put two excitations on the qubit because of the nonlinearity of the qubit. Okay, you have to stay. So we have two excitations. Are the excitations going to move around this way, or are they going to move around maybe the other way, or what's going to happen? Okay. I always ask this question and no one knows. But that's great about physics, right? It's sometimes not so obvious. So here's what you do. You have two excitations. So this is a single case where we had a pi over 2, so it's blue. In this case, it's blue, red, green. And now it's with the same phase, and now we have two excitations, and blue and green. And then it goes to green and red. So this is blue, red, green here. And now it's blue and green, and then green and red. And then it's blue and white. So this is going around clockwise, and this is going around counterclockwise. So what happens is you can think of this as the circulation of a hole, and then the hole is going to go in the opposite direction, if you like. So, okay. So this is nice. So this would allow you, hopefully, to build simulators of interesting things like a electron in a magnetic field. Okay, so we thought about that, and we have to build a lot of qubits to get there, but one might be able to do some very unusual simulations in doing that, where instead of electrons in a field, it's photons in a gauge field. And hopefully we can eventually get to that point and do that. Okay, questions? Yes.
So are they fermions or bosons?
Well, these are kind of bosons, if you like. Of course, they're blocked by the nonlinearity of the qubit, so you can only have one excitation on a site. So, but you can still see the effect of a gauge field.
What exchange statistics?
Yeah, you don't have the exchange statistics, so you would have to probably program that in, I assume. But you're building up the capabilities to look at these kind of things. Okay. So that's what I had for, okay, good. That's what I had for the Gimon. We're going to talk about it a little bit more in the next few slides. We have some more data on the Gimon, how we're making it work better. I want to go and end my talks with our quantum supremacy experiment. Yes, go ahead.
Maybe just back to the
Sure.
first one. So presumably, like the kind of one of the goals is to see like fractional quantum photons.
Yeah, then look at that kind of physics.
So what types of signatures would you be looking at, say, if you had a large enough lattice to program the gauge field?
You can, so there's been a lot of experiments that we did that you can go ahead and interrogate the states, and which I'm not showing about here. But basically you have full measurement capabilities of your states, and you just go in and decide what kind of quantum expectation values you want to measure, and then you can do that. But you can go in and interrogate the quantum states. So I'll maybe show a little bit of that in the next slides, the kind of things that you can do. But generally, you have it's your decision on what you want to look at. Well, and I guess you can do even average ensembles if you want. Okay, so I'm going to talk about the quantum supremacy, where we're going here, and I'm just going to go back for a second and talk about the error correction that we were doing before. And when we were talking about error correction, we needed a lot of qubits, but we also needed to have a low error rates. Okay? And I was talking about something like, let's say 10 to the minus 9 errors or so, which is where we're going to be and we're needed for the first applications. And I said something like 1,000 qubits and 10 to the minus 3 errors. So this is kind of a target of where we want to go. Now, when you look at the error correction theory, of course, if the error rate's lower, it's great. You have fewer qubits. That's nice. And then if the error rate's higher, you need more and more qubits to correct this thing. And what happens is the number of qubits blows up at the error correction threshold of about 1% or so. This is for the surface code, but it's generic enough to understand that. So, this is where we have to get. And of course, if you have qubits that are above this error rate, I'm going to call that you're in the death zone, where you can make an infinite number of qubits and you can't build an error-corrected machine. I mean, you really have to do that. So we have to do two things, number of qubits and limiting error. And I call this kind of error correction gain. Below the threshold, it's kind of like you have error correction gain is you can't do anything with it. As soon as you have some gain, you can do something. Like transistors, once you have a gain of 10 or 100, then things get interesting. You can build real systems. Okay, now, this is where we're at. One of the interesting things that happens at Google is we're a company, and you think about a little bit about marketing, and you see what's going on in the field, and there's a lot of marketing going on in our field right now, which is kind of a little bit disturbing. I'll tell you why. And one of the marketing things that happened in the last year or so is everyone talks about how many qubits they have, which is great. You know, people are making a lot of qubits. That's really good. We need to do that. We're doing that too. But if you're just talking about the qubits, it's kind of like you're down here where qubits have error correction gain, everything's working well, and we're just trying to get up to here and whatever. But that's not where we're at all. Where we're at in the field, and this is a serious thing we have to do here, is we're up here at, say, about 5% errors. And although it's great, you have a quantum computer, you can run things, talking about quantity kind of doesn't make too much sense, because if you have 5% errors, you can do maybe 20 or 40 operations before the quantum state loses its memory. You know, and 20 or 40 operations, I don't care how many qubits you have, that's not very much. Okay? So, in my view, you know, we're here and that's great and whatever, but what we really need to do is get down in this direction and, of course, increase the number of qubits at the same time. It's hard to do both at the same time. That's for sure. And we have to get here. So this 9 qubits, about 0.5% errors, a little bit more than that. That's what we started with at UCSB when we moved to Google. Okay, what we're trying to do with the quantum supremacy experiment, and I'll explain what that means, is get to this point here where we get to about 50 qubits, about 0.5% errors, maybe a bit more, get below the error correction threshold, and we'll show quantum computer is powerful. And I'll say what that means. That's our big goal here, because it's the easiest goal within reach. It's a crazy hard goal, but it's within reach of where we're doing, what we're doing here, and it gets out of this quantity hype regime. And then at the same time, we're looking, this is going to be a powerful machine, we're going to look for near-term applications. Okay, and we actually want to do a cloud offering, all the standard things, and encourage people to look for that. In fact, we do have one kind of minor, but we actually have a near-term applications that's associated with this now. But we want to look for more obviously. And then we're going to get down to here, 10 to minus 3, 1,000 qubits, move down in this direction to do error correction. And then for a full quantum computer, you're going to need maybe 1 million qubits or so and do better here and get down in this regime where there's lots more things to do. So, you know, there's our trajectory. Okay. So the first thing we have to do is focus on making better qubits, scale them up. And, you know, I would say this quantum supremacy experiment is kind of, it's almost like a management tool for me to motivate people to really focus on what's going on. Just to get back to this quantity hype a little bit, just to show you some real data, what people are doing. IBM has, and Rigetti have about 20 qubit machines. These are hard to make. It's really wonderful. They put them online and whatever. I want to talk a little bit about what actually is the error of those devices. And this here is an integrated histogram of their 2 qubit gate error. So when you have 20 qubits or so, you have a bunch of gates, and each one of these vertical lines represents the fidelity that they measured for that. And what you see here is that there's typically a broad distribution. It's hard to get everything to work at the same time fine. And although, you know, people quote the best values of maybe 1% or a little bit worse than that, what of course matters in a real algorithm is the average. What's the average, what they're doing. And if you look at here, the medium or average or so, that's something like about 5%, maybe 10% for here, okay? The 5 qubit device we had here, which is way simpler, so it's kind of not a fair comparison, but we were between 0.5% and 1%, okay? So we're trying to take this, which we think is better, hopefully in the long term, trying to make a more complicated device and make the fidelity good, but no matter where we are here, we have to get down here at their goal of a few times 10 to minus 3. So we have more work to do. Everyone does. Okay, and we're hoping that, you know, we're a little bit closer, it'll be easier, but okay, everyone has a lot of work cut out for them. Okay. So what's the point of the quantum supremacy experiment? What we're trying to do here is run a quantum algorithm with about 50 qubits or so, and we're going to get some output of that. And to know if that output is correct, we have to do a classical simulation of the quantum circuit. And because this is so big, you're going to have to use a big supercomputer, large amount of processing power to do that. And in fact, the time to check it is going to be way longer than the time we're going to take to measure it. Orders of magnitude longer, and then we say, okay, quantum computer is powerful. We're not saying it's useful yet, although there is a small application, but that's it. So in terms of why we're doing this, I hope I motivated that with the last slide. It's kind of funny, some of our competitors are talking about this as purely a marketing exercise, which is kind of funny. But it is kind of true, because when we talk about this to Google executives and Silicon Valley engineers and executives, they kind of get it, that this is showing that it's powerful and that's an important thing. In fact, it's okay that it's not doing anything useful to them. And you have to realize people outside of our field have been listening to the hype of quantum computing for years and years and how powerful it is, and then all they hear about is entanglement of two photons and what the heck does entanglement mean anyway? So they hear all these words, but this is something they can understand. So it's actually useful. However, in terms of the technical reason, I really like this one. We assume that when we have a lot of qubits and we build everything properly, we're going to be computing on a gigantic Hilbert space that goes as 2 to the n. My statement is, and of course the whole power of a quantum computer is dependent on that. What experimental evidence do we have that this is really true? Does nature really allow us to do that? And if the world is going to be spending tens of billions of dollars, maybe we should try to prove that fact as soon as possible. I think that would be good for the field. And you basically want to know, well, how big of a Hilbert space can we be computing on? And demonstrate that, which this experiment will do. I think is a very good thing. The other thing is, you build something like this, and how do you know your quantum computer is working? So in computer science, they have this thing called the Hello World code, where you write just simple program, and then you run it on whatever computer you're bringing up, and when you get the output, okay, the whole stack of everything is working properly. And I'm going to say that this represents some kind of Hello World experiment that proves your quantum computer is actually working properly, okay, and things are right, in a detailed way, okay. So here's the algorithm. This is a little bit complicated, but not too much. Let me just step through this. And this is the schematic of the sequence, okay? These X's are single qubit gates, and these two lines here are the control Z. It could be a C naught, but let's say a control Z. And then you're going to run basically a generic algorithm. Any quantum computer program that you're going to write is going to fit into this, where you have single qubit gates interspersed with 2 qubit gates and then single qubit gates. If you have 2 single qubit gates here, you in fact combine them together. You know how to compile them together. Okay, so it's a little bit, you would do that. But this is generically the way you're doing it. And you start with the 0 state, and you run this, and then you measure the output, as you would in the thing. Now, what happens in the quantum supremacy is that these single qubit gates they're known, but they're randomly chosen from these Clifford gates and also a non-Clifford gate here. And these are chosen, they're known from CZ gates. And because these are randomly selected, it's known, but kind of random gates, the state we're going to get here is basically a random state. Okay, you're going to get all possible probabilities that are coming out of there. Now, although that doesn't sound very useful, in fact, there's a property of these quantum random states that we're going to use that makes it very powerful. Okay? And I'll talk about that in a second. So basically, we run the quantum computer, we measure all these outputs, and let's say we can do that, maybe sample 100,000 times in about a second or so, maybe a few seconds. So that's really fast, running quantum computers fast. And then, because there's no structure in this problem at all, you can prove with computer science arguments that, look, there's no structure. The only guess you would have out of this, that any outcome k here is probable, and you know all the ones are probable, and all you know is that it's going to be uniform. However, that is not what happens. What happens is the output probability here is speckled, and that means some probabilities are higher and some probabilities are lower. And that structure is what we're going to look for in the algorithm. Go ahead.
So when you say it's completely random, let's consider if the depth is only relatively shallow. And
Yeah.
since you're applying only a finite gate set out of the full
Right. Yeah. So if the gate is shallow, it will not get random. And I think the depth you need to make it look in the specular way is about 5 or 10. And it turns out that you have to have a depth of about 40 or 80 to make it computationally complex. So you're well in the limit of doing this. Okay, so to explain what do I mean by this speckle, I'm just going to give an example of a laser pointer with a frosted glass in it. Okay, I bought this laser pointer in China because it's a fraction of a watt, and thus it's illegal in the U.S. And karma is great. When I bought this, they stole my credit card number, but we fixed it right away. But okay, fine. It works fine. Okay. And we have a green laser pointer. It's going through a frosted glass. It's taped here, so it's safe. Okay. And of course, this frosted glass is going to diffuse out the green beam. So when I point it here, you're going to see a green beam. Okay? So there we go. You see the green bean. But I hope people in the front and I hope people in the back, you can see that there's a speckle here, in that some directions it's really bright and some directions it's very dim. Okay, and of course what's happening is you have a coherent source, and the coherent is going through the frosted glass in a complicated way, and some directions the different paths constructively interfere, making it bright, and some directions they destructively interfere, it's getting dim. And it's nice because just by seeing the speckle, you know that your light source is coherent. Okay, so that's kind of cool. Like if I had a white light, you wouldn't see this. And then the other thing that you can see here is that if I knew exactly how the frostedness works, I could predict where it's bright and where it's dim. Okay? And the prediction of bright and dim is going to tell me something about the fidelity of me being able to control this and know what I'm doing. So in fact, in the quantum supremacy experiment, we're going to do both. We're going to look for speckle, and we're going to look for the prediction to see if everything makes sense. So that's essentially what we're trying to do. And to check this, it's a very simple idea. To check it is you calculate what you expect. You've randomly chosen these gates, but you know what they are. From that random choice, you run it. You run the Schrödinger equation or do more complicated things to make it more efficient. You measure, you determine what the probability is for each of the outputs here. Let's say you store in a lookup bed. This might take days and huge storage, whatever. And then you compare it with a cross-entropy correlation, where you look at the probability. This is what you measure, K. And then you go in your lookup table and say what you calculated, P. And since the measured values are going to be the bright ones, you're expecting, when you plug it into this, These are going to be the high probability cases, which are greater than p-classical, and this is going to be greater than 1, and you're going to get a more positive entropy, cross entropy. That's the idea. Yes?
You can do this without sampling too much of that 2 to the n.
Yes, and that's what's nice about it, is you can sample. You don't have to sample all 2 to the n possibilities. You can sample 1,000. Those 1,000 probabilities you expect to, again, be the brighter ones, and then you can see if it's correct. So that's nice. It's actually works with sampling. Good. Yes?
For a finite number of sampling, how does the fluctuations affect?
So you can do that, and then basically you're going to have a 1 over root n statistics between it working and not working, and you can work out the statistics of when it's, or you can do an experiment and measure it a bunch of times and show that it's significantly significant. But you have to worry about that. But, you know, the nice thing is it takes seconds to take the data, and of course you have to check it, and that takes a long time. But, you know, so the thing is if you do quantum, you get a positive value. Here's the classical if you randomly guess. The cross entropy changes by 1 between quantum and classical, and that's actually a pretty big signal to look at. Okay. But, you know, you have to do the statistics properly. We think 1,000, 10,000, 100,000 events, few seconds, you'll absolutely know as long as it's working right. So that's the idea. Okay. Now, you have to talk a little bit about the physics of this. How does this work? So how does this speckle pattern work? And it basically happens that when you're looking at the real and imaginary part of the wave function, or in the electric field, the electromagnetic field in the x and y direction, it's the same argument. It's going to be Gaussian distributed, centering around 0 because of all the randomness in it. But it's going to do it in this component and this component here. And the intensity, the probability, is going to go as the radius squared. Okay? And you see that given these 2 distributions, you're going to have a distribution of probabilities. There's going to be a lot of probability, a lot of events, events at low probability and few at high probability. And if you go ahead and do this for, I think this is like 30 qubits or something, this is the index k going from all zeros to all ones. And you plot those probabilities, you see this kind of distribution as you expect to hear. There's a lot of low probabilities and few high probabilities. Okay? Make sense? Okay, and in fact what you can do is take these probabilities and just sort them from low to high and then plot them. So this is low probability to high. If you tilt your head, this particular curve is actually the probability distribution, which is an exponential e to the minus p distribution. So this kind of physics here is known as a Porter-Thomas distribution, exponential distribution. You see it in speckle, photon speckle, this speckle. Okay, that's great. Now, this is what's kind of cool about this algorithm. If I have a speckle that's given here, okay, and I just change things a little bit, okay, this is a complex enough interaction that the speckle pattern completely changes, even with one change. So I have this big thing, I just put in a bit flip or a phase flip anywhere, the speckle pattern is, it's there, but it's completely changed. It's totally uncorrelated with the prior speckle pattern. And you can look at that statistically. You can put one error anywhere and look at the distribution, comparing it to the old one, and it's basically flat, like. You've totally lost the coherence. There's no correlation anymore. Yes?
Sorry, what exactly is plotted in the blue line? Because I could imagine one error being just like a dip, replacing one of the gates to a different.
Yeah, but what's happened is we're doing that, and then we're averaging all the errors. So you're using the same index as before, but by averaging all the possible places for the error, it averages to the classical. But the point is that you lose correlation, okay? So what it means is that we have an algorithm that is sensitive to one error. in our algorithm. And that is really useful experimentally. It's hard to get it to work, but it also allows us to measure if we have an error in our algorithm, which is something we want to know. Okay? So here we go. S total is the probability of no error, and we have an S quantum. S classical is going to be one difference, and it's a probability of no error. So for an arbitrary circuit with errors, you can then compute what your entropy is. So you can compute the probability of no errors. It's basically e to the minus the total number of errors, both from single qubit measurement, 2 qubits measurement, all the errors, you just sum it up. Okay, remember we talked earlier about how you want to use this model where you kind of think of it as probability of errors, and this shows that you can kind of use that idea, just sum up the chances of all those errors, and then you know what's going on. So this is great. This probability is going exponentially with the number of errors. So I'm going to plot an exponential. So this is the cross entropy S total minus S classical. It goes from 0 to 1. This normalizes it. When there are no errors, this cross entropy is 1, and then this goes to 0 once any gets before a few. And we have to do the statistics properly, but what you're going to do is you're going to see if you get a non-zero cross entropy, and as long as the number of errors is less than a couple or so, you should be able to statistically prove that okay, the thing is working properly. And we'll know how many errors we're making. We can measure that. That's really kind of cool. So in fact, we're using cross entropy right now as a way to do metrology on our qubits. It's a very generic way to test whether they're working properly, because you can know when you have one error. So will our quantum computer crash? 49 qubits, maybe depth 7 or so. You have to do more depth than that, but just take depth 7, 0.5% error per, the total number of errors is of order 1. So it's kind of within rough limits of what we can do. Okay, we have to make things a little bit better, but within range. And of course, what we need to do is have scaling and low errors. So it's not this way far out thing we'll do in 20 years. It's really something we can think about doing now. So that's kind of the idea. Okay. So to check this idea, we did it with a Gimon experiment, which is the next version of the Gimon with 9 qubit Gimon device. Okay, similar, and we have the couplers between them given here and the readout given here. It's kind of a hybrid between the Xmon and Gmon. And here we have the Hamiltonian, it's h dot sigma. And then we can do a swap interaction between neighboring qubits, G. And all this is controllable. The H has about 200 megahertz energy that's controllable. G is plus or minus 30 megahertz. The time scale, what we can change thing out is about a nanoseconds, but it has about 20 microhertz coherence time. And all of this can be calibrated to about 100 kilohertz or so. So if we're in the 10 or 100 megahertz, we're at 1 and 0.1% calibrations. So that's really good. But again, that's the thing that took a year. I want to notice there's something like crazy here that's going on, is that we're going to be calibrating this with this qubit coupled to this qubit and everything else off, and then this qubit coupled to this qubit and everything else off. So that's how we calibrate the G's. But when we run them, we're going to be turning all of these on at the same time, which is running the quantum computer in a way that it was not calibrated for. And, well, is it work? Okay, so basically it doesn't work until you really understand what's going on here and you can model things properly with all the various interactions going on, so that the single qubit calibrations tells you all the parameters. But all these G's can get turned on at the same time. They're all interacting. You have a 9 qubit interaction at the same time. and we know what's going on there. That's what the experiment's going to prove. That's, it's kind of crazy. So we're doing the quantum supremacy. Yes, go ahead.
So, but your pulse sequence still ends up being like single qubit bits and then 2 qubits.
Yeah, I'll explain the pulse sequence. It's a little bit different pulse sequence here because we have to kind of tune it into what we're doing. What we're going to do here's with 5 qubits. It's kind of like the simulation experiment we did earlier. We're going to do 2 pi pulses that put 2 photons. So there's a photon excitation here, 0, 1, 0, 0. Then what we're going to do is change the qubit frequencies in a known, but we'll choose that. Okay, so we'll choose whatever the frequencies are. And then we're going to pulse on the interactions which more or less are eye swaps, because some of them are longer or some are shorter. It's randomly choosing, random but known choice of the eye swaps. And all of these are getting turned on at the same time. So you have a very strong entanglement of all the qubits at the same time. So it's similar. It really follows the basic needs for the quantum supremacy, but it turns out this was just easier to do. One of the nice things here is this eye swap is photon conserving. This is photon conserving. So you expect 2 photons to come out of here. And what we're going to do is we're going to post-select to 2 photons, make the data a little bit better, but we're throwing away maybe 10, 20, 50% of the events by doing that. Not throwing away a lot of events. We're throwing away a few events. Okay. And of course you repeat many times in the same way that you're doing that. So that's the algorithm. Okay, so for 5 qubits, 2 photons in, 2 photons out. Here are all the possibilities. 0, 0, 0, 1, 1, all the way to 1, 1, 0, 0, 0. And this is for one particular instance of the frequencies that we chose and how we connected them up. And you see all the probabilities here. There's only, 10 states here. It's easy to get the probabilities. And the first thing I want to notice here, is the probabilities are not constant, right? There's a lot of low ones, few small ones. It looks very speckly, okay? That's what you wanted, okay? And then you change the instance, so different frequencies, different couplers, coupling strengths, or whatever, you get this, it's completely different. And a third, completely different, a fourth, completely different. So you see the speckles, you see it's dependent on what you do. It kind of makes sense from what you expect from a quantum system. Right from this data itself, you would think that there's good quantum coherence in the system because you're seeing the speckles. Okay. Now you can look at that in more detail. Okay. And what you can do is you can, for example, in 5 qubits, there are 10 states, and you can histogram the probability of the number of counts that you're going to get. And you see that there's a lot of states that are at low counts, low probability, and there's few times that they're high caliber. This is taken with many instances, thousands and thousands of instances. And then when you go to 6, 7, 8, or 9, this, of course, sharpens up because you have more states that you're looking at. The interesting thing is to take this raw data and scale it to the probability times the number of states, and then you get on a universal curve that's basically exponentially decaying here. So it collapses to an exponential distribution. Again, that's what you expected. Right? You expect to see an exponential distribution from these Porter-Thomas kind of states. Okay? Now, notice there's a little bump here. What's going on here? That's actually not too hard to understand. And what happens to kind of see that is this is after 5 cycles or so. If you do after 100 cycles, say the 7 qubit collapses to this kind of Gaussian curve here, which is really moving towards a uniform distribution where you lose the speckle and it's just a diffuse set of qubit states. And basically when you lose coherence, you lose the speckle. That's what you see here. And you're seeing that a little bit going on here. You're seeing losing a little bit of your speckle because of the small amount of decoherence in the system. So you can actually plot that difference from the exponential distribution versus number of cycles, okay? And if you have 0 cycles, okay, it's not an exponential distribution at all, so the difference is big. By the time you get to 1 and 2 cycles, it's really pretty close to an exponential distribution. And for this particular case, where we're turning on all the couplers at the same time, it's very easy to get these states to randomize into the Porter-Thomas distribution very quickly. And then you go longer, and it gets worse, and that's just due to the decoherence. So it's nice, this 9-qubit interaction. You kind of get a full entanglement in about 2 cycles or 90 cycles. It's very, very efficient. Yes?
So then per instance, per cycle that you're doing, you're changing like the qubit frequencies and then you're pulsing them backwards as you change qubit frequencies?
So yeah, if you go back to the plot of what I did, this particular one is we set the qubit frequencies and keep them constant the whole time. And then we just pulse on the swap gates.
And that's the same pulse for every coupler?
These are different lengths. So this is 25, 21, 26, 23. So this is where the randomness comes from.
Yeah, so the way I'm trying to understand this is that each of those pulses is an iswap interaction between
Right.
qubits?
Well, the 25 nanoseconds is ISWAP. The 21 is a little bit less than an ISWAP, and the 26 is a little bit more. So again, they're all calibrated, but we make a range. And that's where the randomness is coming from.
And then per instance, the qubit frequency is the same, but you're changing the
In the instance, we change these frequencies and we change this. Those are the things we change.
So it's a new calibration per instance?
And we have to calibrate all that. We know calibrations of everything. Yeah. Yeah. Thank you. Thank you. That's good. Okay. So we know what the pulses is. We can do a numerical integration of the Schrödinger equation, and the red dots are from the model, from our calibrations, what should it have done, and this is what we predict. And where it's low, the predictions are low, and where the high, predictions are high. You see the speckle pattern really matches what we expected. And again, this is what took a long time to get all that to work properly. That's not easy. So if you take, 5 qubits, versus number of cycles, it starts getting entangled here or here. You do the normalized cross-century fidelity, where 0 is a random guess, and 1 is a perfect prediction. You see for 5 qubits over a modest number of cycles, the fidelity here is 80, 90%, really high, because it's really matching very well. And of course, as you have the number of cycles go up, then you have more errors, and it more or less follows what you expect. The longer the algorithm, the more errors you're going to get. Okay, and it's about 1.8% error per cycle. So by the time you're at 10, you're almost at 20%. Okay.
T1 decay excluded?
Excuse me?
Just over there, the T1 decay.
Yes. So remember, I chose only for 2 events, 2 photons coming out, and we're throwing away, fraction of the events. But you have to remember that that's been kind of post-selected out. That's just the way it's just what's happening. You do from 3 all the way up to 9. As you go to more and more qubits, the error gets bigger. And basically, you see that all the errors scale as the gate and cycle, and it's about 0.3% per gate per cycle, excluding T1. And it's going to go about to 0.5% if you have T1, because about 50%. Okay. So this is comparable with what we've done with the XMON. It shows that we can do all this complicated calibration and get that working properly. Okay, so that's good. And if I extrapolate 45 qubits, it's going to go down something like this. A few number of cycles, we should be able to see that. So we're working hard to move forward. Clearly, we want to make things better. One of the interesting things about this algorithm is that you can use it to tune up your system. It's a very good measure of the fidelity of the system. So what happens is when we measure our system and calibrate, we know all the parameters, but there's a low frequency flux drift in our qubits. And you kind of want to tune that up all the time. That gets hard to do directly. And what we do is we actually use a fitting algorithm where we're tuning up the flux offsets. Actually, we're tuning up the qubit offsets over time. And what happens is we start, in this particular case, at about 20% error, running a particular algorithm, and then we run the algorithm and we just tune, using simple Nelder-Mead, we tune those flux offset over time to try to make things better and find better. So initially it gets worse, and then it figures out what it's going to do, and then over time it gets better. So we've improved the fidelity by about a factor of 5 by small changes in that. So it can be used to tune it up. And those of you who are worried about whether we're using the physics itself to tune it up, let me say there's a way to do this where you don't cheat. And this is actually known in Google when they do machine learning. What you do is you have a separate training data set from what you're doing to test. And what happens is the black is used to find the optimal parameters. The black is a totally different set of benchmarking data used to verify, and everything follows each other very closely, so that by the time we know that the training is better, other instances work well too. So you can do that in a proper way. Okay. So I'm now going to talk about, we've done this hello world experiment to make sure the thing is working properly. Okay. Let's do some experiments to kind of test some new physics. Again, these are toy problems, but okay, that's what we're going to do. And what I'd like to do is talk about the Hofstadter butterfly problem, which is proposed by Hofstadter in the mid-60s, I think. And basically, you think about a two-dimensional sheet of atoms. Here, I just draw graphene because that's very easy to see. And we're going to put on a magnetic field, okay? And then we're going to say, what's the energy spectrum of that two-dimensional sheet of atoms versus magnetic field? And when you solve that, actually the Hamiltonian's not that complicated. The interaction of the atoms, you get the sigma plus, sigma minus. So these are the hopping terms. And then from the interference of the magnetic field in all the loops, you have, for each of the qubits, you have a cosine of a normalized magnetic field changing the frequency of the qubits. And note, this is transforming a 2D problem into a 1D problem by using the proper gauge of the magnetic field and the symmetry of the system. So this is not too hard to solve. It's just you find the eigenvalues. So for 150 lattice, this is the energy of all the excitations versus magnetic field. One of magnetic field corresponds to one flux quantum in here, which is about 10,000 Tesla. And of course, you can't get 10,000 Tesla in the lab, so you solve this other ways experimentally, or you do computation, or maybe you solve it on your quantum computer. The spectrum here, of course, is periodic in a flux quantum, but really interesting in the sense that you have these bands where there are no states, and you have this fractal-like behavior where there's bands and subbands and lots of structure in here. So it's a very complicated, full of structure problem that's very complicated to solve exactly. So this is a nice thing to do with a quantum computer, our quantum computer, because we have a linear chain, we have hopping terms, and we can change the frequency. This is exactly kind of the problem we were solving before. If we solve that other problem with the calibration, we should be able to do that. Okay, so for 9 qubits, this is what you expect theoretically. And it's nice because you see these bands where there's very few energies, as we saw before, and we see lots of complex structure in the energy here and here, everywhere here. Okay, so let's program our quantum computer and let's see how close we can get to this. Okay, there's a lot of structure here. There's a lot of data points. You have to program this for lots of different magnetic fields. So you have to do the experiment many times. Okay, so, okay, what you did. So when you run the experiment, the dots are the data points. And you see they kind of overlap pretty well with the theory. And we've actually color-coded the difference between the experiment and theory here. Most of these are black and green, and that's about 5 megahertz or so errors in here. But you see the gaps, you see all the structure of these things going up and down in some complicated way. Okay. Up here at very high oscillation frequencies, it starts to screw up a little bit more. No surprise, because that's a very high oscillation frequency. But basically, you see all the structure.
How was the spectrum measured here?
I'll talk about that. We actually know how to do this better now. There are some small errors we discovered, and we know how to do it better. But okay, it works pretty well. Okay, how do you measure this? Very basic idea is if you have a bell and you want to know where the oscillation frequencies, you strike the bell, say anywhere, and you listen anywhere, and you're going to hear all the tones of the bell. And if you happen to strike at the wrong point, you may not hear some of the tones, so you're going to strike it somewhere else and then listen there. And by listening to the tones at a bunch of different places, you can then figure out what all the eigenmodes are. So the way that you do that, similarly, is you have all your qubits. You strike the bell by essentially doing a pi/2 pulse. And then you let it evolve in time, and then do a second pi/2 pulse to get a Ramsey fringe. And then you just look at that probability versus time given here. So here's, and you can do it a tomographic way. They get sigma x and sigma y via this Ramsey fringe kind of thing. And you see it's oscillating in this crazy kind of manner. Okay, so and that's telling you how this excitation is spreading out among all the qubits and oscillating with its eigenmodes and doing all that. So if you take sigma x plus I sigma y, which is the response function versus time, and then you Fourier transform this, okay, you get this curve right here, and you can see that there's definite tones here that you see. Even though this looks crazy complicated, you see definite tones here that you would guess are your eigenmodes, okay? Now, like I said, you have to be careful because maybe you're striking it in the wrong way. So what we do is let's just repeat this, striking this, doing the Ramsey fringe at all the different qubits. And when you do that, you get the following data. And you see some of the peaks only are there for one, but many of them are there on all the different the qubits. So you just take kind of the average of that here by taking the average of this, and then you see the 9 big peaks here. And like this peak here, you see it oscillating in almost all of them. This one here, it's oscillating almost all, not necessarily all of them. But by taking the average, you can pick out the nine peaks. And those are the peaks that we picked out and plotted on the other one. Okay? Now, when you pick out those peaks, you can start doing a lot of statistical physics of what's going on there. You can take out the peaks, you can look at the energy level separation, you can look at that energy level separation, you can see how uniform the separation is versus the amount of disorder in the system. So how much detuning did you have compared to the swap interaction? So this is how much detuning there was versus the swap interaction. And as you change that ratio of disorder, you can see the level separation uniformity changes in some way. I'm not going to go into this. I just want to show that you can pull out, I think it was a question of, what can you measure with this? Once you measure all these quantities, you can pull out a lot of information here. So this is some probability distribution for the energy level separation in different limits of delta and J, and you can compare it to lots of different theories that explains that. So you can analyze that in some careful way to understand what's going on. What's also interesting about this is not just singing at a single excitation. You can see what happens when you put in two excitations, because there's going to be interactions between the excitations because of the qubit thing. So what you do is you just do the 2 qubit excitations and then look at these 4 quantities, which you have here. And then it turns out if you Fourier transform this particular quantity here, then you're going to get the spectrum. And I won't go into the math from that, but there's details in the paper here. So here are all the different combinations with the Fourier transform in the way we did here. Here is the average excitation spectrum, and you can find 45 energy levels there to know what's going on. So you can measure all this in great detail. And this again, I won't go into this in detail, but you can look at the energy separation between this versus the disorder and get moments of the probabilities. And basically you see that disorder causes the eigenstates to move towards the center of the energy band, to be pulled into the center, and also into the lattice. When you have a 9-qubit lattice, most of the states are localized there. Okay, so you can just to give you an idea that you can get that information. Once you have a fully programmable quantum computer, you can find out all that stuff. So I have a couple minutes left, and I just want to talk about where we're going. Okay, so we've been working 4 years on learning how to scale up this thing properly. And what we're looking at here is the bristlecone processor, which is a 72-qubit device. It's a square array of the transmons. These are the Xmon transmons, square array, where we put the resonator in the neighboring cells so everything fits together, and we've been able to bring the wires in. So it's a large number of qubits. This is the picture of the bristlecone device. This is our carrier wafer, which is made separately than our qubit wafer, and there's wiring on the outside that comes into here, and then with indium bump bonds we connect to a 72-qubit array and here. And of course that array is flipped down, wiring is flipped up, and you can't see anything. But that actually means that the design is good. I mean, that means it won't radiate and do other bad things. So that's what we're doing. This is how we're mounting it. This is on a 48-wire device, a smaller device. Again, here's the qubit chip. You can now see all the structure. It's bump bonded to a carrier wafer where the wires are coming out. That whole thing is put into a circuit board, and then we wire bond to the circuit board all the wires that go around there. And then those wires go out to coax connectors, so we can control everything. Okay, and this is kind of scalable. This is all this connection here. For those of you in the field, these are up to 1,000 wire bonds in the latest device, which sounds like a disaster if you're a graduate student, except for the fact that we bought an automatic wire bonder. So it's really nice. And it takes about, I don't know, an hour, but okay, you do it. And here's Marissa taking the chip which goes in here and all the connectors and kind of wiring it up in the dilution refrigerator. And this is the latest picture of the dilution refrigerator with lots and lots of wires going from the mixing chamber all the way to room temperature, with a whole swarm of wires connecting up to the qubits. And then those wires go up to a big panel, breakout panel, with 100 or more, a little bit more than 100 wires here, and then that's connected to our rack of electronics, and that's all computer controlled. So scaling up to hundreds of wires, we've been talking about this for a year. It doesn't bother us. There's a lot of issues about reliability you have to solve, but we're working towards that. And this device is getting tested and whatever. You have to write a lot of software to get this to work. And of course, there's a lot of things you have to get work at the same time, so reliability is a big issue. But it's ongoing and we're working on it. I'd love to talk about what's going on, but we're kind of waiting until we get a more, final result before we talk about this in much detail. I'm going to, one more thing before I close my lectures. I want to talk about something that I find really exciting is there's a lot of things going on the algorithm end that is kind of motivating us to build a big quantum computer. And I wanted to talk about these recent results on quantum chemistry. That's really cool. And what happened is Feynman in the early 80s started talking about building a quantum computer. And one of the obvious things he talked about is use a quantum computer to calculate quantum systems, and in particular, quantum chemistry. And, so that was in the early 80s, kind of proposed that. And there's been a lot of progress recently on that. And it's kind of interesting progress. I would say it took about 20 years or so for this paper, some other papers too, just to say that, you could translate a quantum problem, a quantum chemistry problem, into a quantum computer in a way where the quantum computer doesn't need an exponential amount of resources, which is what you need classically. So that was a very big thing here. And then over time, people have been looking at that idea and getting more and more details to it. And it was in 2013 in this paper here where finally, you could kind of write down what the algorithm was. Okay, and that's a really big thing, very, very concrete. That's the good news. The bad news is this is an order n to the 11th scaling. So when you work to Google, you know that order n to the 11th means it will never work. Okay, so you can see that here. This is the number of orbital basis functions. That's more or less n. You need 50 or 100. N to the 11 says you need n to the 11 or 100 to the 11th operations. Okay, that's the age of the universe or something. That's insane. It won't work. Okay. But over the years, it's been great. People have been working on it and bringing that number down to here. It's n to the 6. Just a couple years later. What is this? 1 year later. Okay, n to the 6. And then recently, you've seen there's a series of things here that have brought it down from, n to the 5th. 6 you see is still like a year. That's too long. And then over the last few years, it's been brought down. Now exact solution is n to the 2.7 and approximate solution is order n. Okay? And that's low enough that it's like, you could maybe really solve that. So we're very excited about that. Notice this guy, Babish and McLean that's here. We hired them. So, I'm motivating people, to come up with a good idea. We're going to get really excited about it. So here you might need 100 logical qubits or about 1 million physical qubits. We're calculating exactly what you need. It's long farther we want, but it's within range of something we think is really possible to do. And of course, this is real applications that really good. This might need, something more we can do, but they have to be good qubits. So we're looking into that. But it's really interesting that this is a very big general application that we might be able to do. So we're very excited about all those possibilities. I'm just going to end it at that with showing a picture of the group, I think about 2 years ago. We're bigger now. And thank you all for your attention for my talks. Yes?
Can you go back to the slides where you use some learning algorithm to reduce error?
Yes. There it was. It's just Nelder-Mead. I mean, nothing fancy. That's the one you're talking about?
Yeah, so like, then like in one step of this training, like what's happening there? Like,
In one step, you're going to change, let's say, one parameter, and then you see if it gets better or worse. And then based on that, the algorithm the next time goes farther or changes it or you know, just moves it. Nelder-Mead is a very, very simple algorithm for optimization where it kind of just looks locally at what happens with differences and then does. You can do this much smarter, where there's much smarter algorithms than this.
so you're using it for calibrating the parameters or
So what we're changing in each step is a small amount of a flux offset. There's a DC offset to our flux. And what happens is, because there's a drift in the flux offsets from 1 over F flux noise in our system. So that parameter is important, but tends to drift around and not be so stable. So we need to tune that up. So, you know, all the other tune-ups may take days and days to get all the material, the electrical parameters right. And then we just do this at the end to get it good. And this flux offset will probably be good for 6 hours to a day. So we just do it once and we can operate it for a while. But you would want to do it again. And once you kind of know how this is working, it's very easy to, re-optimize it once you kind of know how it's working. I would say what happens is this fidelity landscape is I guess the word in computer science is convex. It's basically a bunch of parabolas, okay? And there's not much interaction from one parabola to the next. So it's very easy to use a gradient descent and find the best thing. It's not a complicated landscape, at least for those parameters. But that's good news, you know. It means it's easy to do this. So we do a lot of automatic optimization with our qubits, and most of the time it's really pretty simple. You just have to iterate. You can do more complicated things, and then you're able to find, you know, optimal performance pretty well, which is good. Yes.
So you showed us some slides back where you can average gate fidelities for the IBM 20 qubit device. We get each of the qubits device.
Yeah, it's a 5 or 10%. Yeah.
The 5 qubit device average gate fidelities look better.
Yeah.
Can you think about the average gate fidelities of like 20 qubit or 50 qubit? Or not?
Yeah. You know, our gates are intrinsically 10 to minus 3 or 10 to minus 4, and it's like 1 or 2 parameter optimization to get the shape. And it turns out you need to choose the frequency carefully to be away from 2 level states, which we can measure and do that. So I think we have this very simple gate, and we can tune it up to avoid all the little bad things that no one in our field talks about that are there. Okay, they're really there, but you can kind of avoid that. And because of that, I think we're doing better. But we'll have to, you know, we have to, you know, make a square array and see how it works to know that. But I'm going to say that that's what's going on. Yeah, so, and because we have to do all this tuning and getting it to work right, there's a lot of software and optimization. So that's kind of why, you know, we've been a little bit slower to get systems out. It's kind of hard to get all this stuff tuned up really, really well. You know, our feeling though is, you know, it's nice those machines are out there, but what people really want is a sub 1% error devices, so that's what we're spending all our time on. And it's hard, and it takes a long time. And, you know, we still have to show we can do it. Okay, that's it. Thank you very much.
Say whether or not the crystal cone qubits are Gimon or typical
The bristle cone are the transmons, the XMON design, yeah, where we're doing that. But we are working on the Gimon device and trying to scale it up. We've made some more improvements, and we're trying to scale it up. So we'll be doing, both of that. But that device isn't, it's harder, and it's going to take some time. But yeah, we hope to do both, which I think even if we, they solve different kind of problems, so they're interesting to have two different kind of processors. So.
The Nelder mead is near and dear to my heart. It made up an obnoxious portion of my PhD. So you say that this sort of takes care of drifts and the offset and you can run for like 6 hours. How long does this optimization take? These are optimization steps. I'm going to guess this is a hour to do all this. Yeah.
But once you kind of know what the derivatives are and kind of know where you're set up, you should be able to re-optimize this in a minute or so.
Because you're more or less.
Because you know
You haven't
what's
gone
happening.
out of your minimum.
Yeah, you know what the parabola, all the optimization things
Have you
work out.
guys tried to do some gradient descent on this? Because Nelder mead is derivative free, if I understand.
And it's basically because you don't have to think, and you just run the thing, and it doesn't take too long. So you do that. But yes, and in fact, in our regular tune-up things, we have tune-up algorithms that are, pretty sophisticated to do that.
You just dive headlong down.
No, you should be able to dive in and get the optimal very quickly. I would say, maybe even seconds.
Okay.
Seconds or minutes. It should be really
So
easy.
you give it a half hour at the beginning of the day.
To get-
Every few
yeah.
hours, you give it another minute or so.
Yeah, and it's essentially, it's a couple hours from knowing nothing. And then let's say every day it might take a few minutes. And then if you even wanted to tune it up every hour, it would maybe take a few seconds. So you have to write all those calculations. But this is totally brute force. This is what's kind of amazing. Which is nice. You don't have to think about this. You just run that. But there are smarter ways to do this, that's for sure. But I would think the most interesting thing is it's very reliable. It's like almost whatever you do, the quantum mechanics is very convex, and you just tune it in and get it to work. It's not like you have to do crazy things to get there.
Yeah. Okay, cool. Thank you.
You're welcome.
In your photon circulation data,
Yes.
so you had some like 3 probability curves. That
Right.
In one, when one of them when they bottomed out, there
Yeah.
was like.
There's some structure to that,
Yeah, the trailing edge was like a little higher than the
Yeah.
leading edge.
Yeah.
Is that just coherent?
I think that's just what you expect theoretically. That there's some, yeah.
That's kind of.
This is my guess. Usually our data is very close to the theory, so I would say that structure is probably there. Because you have an interference of the multiple paths, and it's not like there's no amplitude going to the wrong path. It builds up there, but then it gets taken away from all the other.
Yeah, I guess
You'd have to look at it carefully. Yeah, you'd have to look at it carefully.
Yeah.
So, but my guess is that that's real because generally the structure we see in these things are what you would expect.
And then on the hundreds of seconds time scale, there was some damping.
That's just normal decay and dephasing. But yeah, you could see the oscillations, many oscillations in a microsecond, and the coherence times are tens of microseconds. So it looks very good. But yeah, we're interested eventually to see if we can build big arrays of these things and do.
Boson sampling or something.
Well, you can do boson sampling, but the qubit sampling, the supremacy is much more matched to what we're doing. But look at what fact of gauge fields and look at the complicated physics of that. That I think would be kind of interesting as an interesting quantum simulator. Where there's, I'm not sure, I'm not knowledgeable in how the physics is, but I imagine the physics of that would be very interesting. And you can, test things in a good way there.
So I think a few months ago, people in Alibaba claimed that they can simulate 9 binary lattice of spins.
Yes.
To depth 40, so does it mean you need more?
Yes, the Alibaba story is very interesting. We've been developing code to simulate this efficiently, and We think the limits of what we can do now are about 48 qubits with a depth of around 45 or 48. And that's a pretty hard computation problem. They claimed, with a slightly different technique, but they claimed something like 70 qubits with depth 48 or whatever. But you have to realize that their algorithm is no better than our algorithm. What we did is we quoted the simulation for like 10,000 to 100,000 events, because that's what we're going to do, and they quoted it for one event. So if you're defining your problem to be 100,000 times easier, then it's going to be, your results are going to look a lot better. So you have to realize this is what's going on in the field. Alibaba knew this, we told them this, the people from Wired, other people knew this, and they went ahead and published their stories anyway without clarifying this issue. So there's this really crazy marketing thing that's going on that people really don't care if they're being very clear, but if they can get some headlines and make their company look good, they'll go ahead and do that. So it's a lot of hype. But their algorithm is different. It's kind of nice, but it's no faster than what we're doing. So we're trying to get some real benchmark standards so that people can compare against benchmarks.